Thanks a lot for having me. I will discuss our recent paper S1, Simple Test Time Scaling, and some general thoughts on this exciting new paradigm. And this was joint work with many amazing collaborators listed here, and many others that helped in various ways. During the talk, feel free to interrupt with questions or thoughts at any point in time, and then we can also take more questions at the end. I think we have 1 hour scheduled, but I'm happy to do a bit longer depending on the interest. Great. So a lot of the excitement started with OpenAI 01 in September 2024, where they published this blog post, Learning to Reason with LLMs. And in this post, they released 01. And what was impressive about this new model was its strong reasoning performance. And they showed this on various tasks like competition math, competition code, PhD level science questions, where it was a step level change from prior models like GPT-4o, especially here on math, where it goes from 13.4 to 83.3. So really massive improvement. And the second really exciting part about this release, besides the reasoning performance, was test time scaling. And they had this plot at the top of their blog post where they compare train time scaling on the left and test time scaling on the right. Train time scaling is what has driven a lot of the progress in large language models over the past few years, where more training time compute has led to continuous improvements that we were able to predict with so-called scaling laws. And many people have thought that it would be really amazing if we could do the same thing at test time, because often it might not be worth training a super large model and then use it for some sorts of questions, but rather you might be able to train a cheaper model and then have it think longer at test time and thereby get better answers from the model. I think a very simple example is if you only care about a model that does arithmetic, so it is able to multiply or say just additions, just add numbers to each other, say 1 plus 1 is 2, 2 plus 2 is 4, and so on. Then if you want the model to compute additions like 500 plus 500 or like very large numbers, you'll have to continue in the traditional paradigm scaling up pre-training time until eventually it's able to add almost all of those numbers. And it might be much more efficient to rather have the model at test time break down these very large additions, right? Rather than doing 500 plus 500 equals and off the top of its head, it has to know that the answer is 1,000. You rather let the model break it down to 5 plus 5 is 10, and then count the zeros or something. And that would lead to more compute at test time because the model has to do some additional thinking and going back and forth. But you probably can get there with a lot less train time compute. So it seems likely that for many tasks, we've been allocating compute very suboptimally, like spending a lot on train time and not really making use of test time, letting the models think for a long time. And so they put forth this idea that, OK, we should also scale test time compute, and both of them lead to improvements on AMI tasks, which are these math competition tasks that they benchmark on. So two things that were really exciting to me, and I think many others, the reasoning and the test time scaling. And I think taken together, these have huge promise for solving many problems that I think many of us are very excited about, things like the Riemann hypothesis or big questions in computer science like the PNP problem, or in physics like the string theory. If we have a model that can reason really well, and that reasoning scales with test time compute, so we can let it think for days, weeks, or months, then maybe we have a shot at having these models help us solve some of these exciting problems. And that's super exciting to me and why I really want to work on this area. And in this work, we set out to find the simplest recipe to achieve reasoning and test time scaling. And we refer to our outcome as S1. And the title is Simple Test Time Scaling, but it's also about simple reasoning. So how can we get to test time scaling and reasoning in the simplest possible way, inspired by 01 and various other previous approaches? Break this approach down into the data we construct, which we call S1K, is our data set, a very tiny data set that extracts the reasoning capabilities from a model. And then our test time scaling component, which we encourage via budget forcing, which is a very simple technique that we propose. And together, they lead to our S1 model. So let's start with the data. On the data side, we started with collecting 59,000 questions. And in this collection, we included various data sets that we came up with ourselves. So one is S1 Prob, which is a bunch of statistics PhD questions that we collected at Stanford. And here's an example question: show that the uniform distribution on 0 to 1 is not the convolution of two independent, identically distributed variables. So these are very hard stats questions that PhD students at Stanford have to solve as part of their qualifying exam, and that determines whether or not they can stay in the PhD program. The second data set we created ourselves, which we also include in these 59K, is S1 teasers. And this data set consists of very difficult brain teasers that are commonly used in interview questions for quantitative trading positions. So here's an example question. Suppose you roll a three fair 100-sided die. What is the expected value of the lowest roll? And this is, again, a very difficult question, requires a lot of math and a lot of reasoning. And alongside those that we create ourselves, we also source from a lot of existing data sets that previous teams have collected. For example, we add several crossword puzzle questions. We use a lot of questions from previous Olympiads. So USACO is the computing Olympiad in the USA, and that one is used to challenge high school students and maybe even higher level students for a very, very difficult computer science questions. There's the physics Olympiad that also has very difficult questions covering physics, and various mathematical Olympiads and others. So overall, we create this data set of 59 extremely difficult questions. For some of them, we have answers. For some of them, we don't. But they're all really, really difficult and come from various topics. And with those 59 questions in hand, we follow a recipe to reduce them to a very simple and clean reasoning data set. Specifically, we first conduct quality filtering. So we filter out any questions where there was some issues in the formatting or questions that we thought might not be super high quality, despite that we looked for really high quality questions. Some of them might still not be super great. We also removed questions that we thought were not difficult enough. We collected these 59 questions looking for extremely challenging competition problems, but nonetheless, some of them might not be sufficiently challenging. And the way we conduct this difficulty filtering is we run existing models over all of these questions, specifically Gemini, Qwen, and some other models. And then we record whether or not they're able to get the question right. And then we filter out questions that the small models do not get right, but large models get right. And the intuition here is that we want questions to be solvable. So the best of the best models, say very large models, should be able to get them right, but small models fail because they're too difficult for them. So there's an additional model-based difficulty filter. And finally, our third key ingredient in data filtering is diversity. And what we do here is that we take those 24,000 remaining questions and we group them into categories such as geometry questions, statistics, and then various subfields of statistics, and so on. And then we sample from each of them, ensuring maximally diverse samples in our final 1,000 samples. And another criterion we use here is how long is the reasoning trace for a question if we use a model like Gemini or other reasoning models to produce an answer for this question. So in our first iteration, we used a Gemini to produce reasoning traces for all of these questions. And then our intuition is that the longer the reasoning trace of this model is, the more difficult the question likely is because it needs to think for a longer time. And so that's another filtering criterion that we use here to make sure that the questions are really difficult. So these are our three key filtering steps: quality, difficulty, and diversity. And that leads us to a small data set of 1,000 hard reasoning questions that we call S1K. And in the next step, we use existing reasoning models to distill reasoning traces and answers. So as mentioned, we use Gemini, but we also use DeepSeek R1. And here's a quick example. So we have a question from our data set that's about astronomy. An often repeated fun fact is that humans produce more power per unit volume than stars, and so on. And here's the example trace of Google Gemini. And this is what we used for our initial model, S1, with the data set S1K. And here's the reasoning trace of DeepSeek R1, which is what we used for our follow-up data set we just released recently, 1.1 as 1K 1.1, and then our corresponding model as 1.1. And we'll go into a bit why we switched from Gemini to R1. But you can already see from these traces that R1 tends to be more detailed, and its traces tend to be much longer than the Gemini traces. And this is part of the reason why they're better and led to a better model.
Hi, Nicholas.
Yes.
May I ask, what is the format of the data point? Is it a QA or like a long sentence or something?
Oh, yeah, sorry. The format is that there's a question. So this is what's at the top here. A hard question. And then we produce a reasoning trace plus an answer for that question. So it's just Q&A, essentially. Yeah.
So is the COT generated by large language models, or is it collected in the data set?
The COT is generated by large language models like Gemini or DeepSeek R1.
Okay, so it is a synthesized data set.
Yes, it is a distilled synthetic data set.
Oh, I mean the 1K data set you collected. You said like you collect some problem from Stanford or like some teaser, right?
Oh, I see.
You only collect the problems and you use large language models to produce the answers.
Exactly. We also have answers for some of the questions, but we don't really use them, at least not in our training procedure. We use them sometimes for filtering. Specifically, sometimes we use them to check for correctness based on the actual answer and the generated answer by our model that we distill from, like Gemini or R1. But otherwise, for the final training, we just use the original question from the data set, be it our Stanford S1 prop data set or the S1 teasers, plus the distilled generated reasoning trace, plus the distilled/generated answer.
Then it's like how to make sure like the generated COT or the final answer is correct.
So partly we filter for that. So when we have an answer in our data set, like for S1 prop, for example, we have answers for every question. And in that case, we can check whether or not the answer matches by asking Claude in our case. But we don't do this for all of the samples. And in fact, many samples in our final data set have incorrect reasoning traces and answers. But surprisingly, we found that this doesn't really matter. It's much more important that there's long and coherent reasoning, and it's fine if the final answer is incorrect. It's more about teaching the model this reasoning style rather than making sure all the answers are correct.
Okay, that's interesting. So would like the wrong answer get will you assign like a lower reward for them, or like they are, or like a SFT, or you don't have reward here?
We don't have rewards here. We just do SFT, and we just train on them as is. So wrong and correct ones get the same weight.
Okay.
The goal is to find the simplest recipe, and we found that this, whether or not they're correct or not, surprisingly, doesn't make a big difference. Yeah, we have a bunch of data ablations that we'll go into later, but I also think this is a very interesting aspect. Yeah.
Okay, yeah, that's interesting. So, do you have like an kind of idea, like what's the ratio maybe about the correctness and the wrong ones? I think the correctness must be the majority, right? Correct ones.
I don't have a ratio off the top of my head, but I think it's double digits incorrect.
Okay.
The majority is probably correct, yeah. So maybe 20% or something, but not sure.
Okay.
I didn't compute it. Yeah.
Yeah, the observation is quite interesting. Yeah, thanks.
Also, so if you're doing SFT, then the exact tokens that are in, say, the chain of thought to get to, say, the wrong answer, you're penalizing specifically for not using those specific tokens, right? Because there's no proxy reward model.
Yes, there is no proxy reward model. Which specific tokens are you referring to? The reasoning?
I mean, like, yeah, the actual chain of thought output tokens in your samples for supervised fine-tuning. Yeah,
so during SFT, we compute loss over the reasoning trace and the final answer. So the model, I guess it is, I'm not sure if that's your question, but it is partly incentivized to write the incorrect stuff as well. Does that make sense?
And specifically that exact incorrect statement, right?
Well, if it's part of the reasoning trace, then yes, we train it to write incorrect reasoning steps.
Yeah, but I guess the convention now is that if you use a proxy model, reward model, that two completely different ways of getting to the right answer can have the same answer and have the same loss, right?
Yeah.
And that gives like the model a little more flexibility as opposed to having to sort of specifically walk through, particularly for answers that are wrong. Although I get the idea of like, hey, we're going to try to push the model to sort of think through steps kind of thing. Yeah.
Yeah. So in our case, since it's SFT, we're constraining the model a little bit. We're telling the model essentially, this is the only correct way to solve this question, which is probably why RL methods are better if you give them sufficient compute, because you're letting the model find its own way to solve it and not just telling it this is the right way to do it, especially in our case where sometimes it's wrong and we're training the model to do wrong reasoning steps. Yeah, so in our case, we only do SFT, but I'm very excited about the RL approaches and improving it with that. Yeah.
Okay, thanks.
Cool.
Can I ask one question? You have one chain of thought for every question?
Exactly. Cool. So yeah, there's one chain of thought per question. Let me know if there are any other questions at this point. Otherwise, we can go further, but feel free to interrupt at any point in time. Okay, so this leads to our final data set, S1K, 1,000 high-quality, difficult, and diverse samples. And here are some of the diverse subfields I briefly mentioned: geometry, electrodynamics, very, very diverse across different fields of science and beyond. And this leads to the next part, which is test time scaling. We propose budget forcing, which is our best try at the simplest method to induce test time scaling in large language models. And here's a simple illustration of how this works. So given a question, for example, how many are in Raspberry, the model will produce its reasoning trace. And when it tries to finish, and we'd like the model to think for longer, so we'd like to scale test time compute such that the model uses more test time compute, then we simply add the string wait at the end of its current reasoning trace. So in this case, the model says the number of hours in Raspberry is 2. And then the model tries to stop thinking here because it has produced its answer. So it wants to move on to the response generation phase and then be done. But because we're adding in this test time compute setting, we're not letting it stop and inserting wait. And then naturally, after that, we let the model continue its generation. And of course, it'll try to respect this new wait string. And so it'll be something like, wait, let's reread the question carefully. It'll try to redo something. And in this case, it even fixes its previous answer. So it moves on to recount the R's and lands at a count of 3. And then we let it finish its reasoning. And then in its final answer, it acknowledges its original mistake and says that the final answer is indeed 3. And this is what we do when we want the model to think for longer. Inversely, if we want the model to think for a shorter amount of time, we just cut off the reasoning at any specific point in time. So we could, for example, right after first letter R, just cut off the reasoning there and force the model to move on to the response generation phase. And in that case, the model would be using less test time compute, but it would likely not be a great answer. It might answer 2 or even something else. But it allows us to spend less test time compute. So this is how we can vary it. And we refer to this as budget forcing because we have a test time compute budget in mind, and we force it upon the model. So when the model thinks, either we just force stop it, and specifically here, when we force stop it, we insert this end of thinking token delimiter. So this reasoning trace here, this blue box, behind the scenes, it is enclosed by a start of thinking and end of thinking token. And we just force the end of thinking token to appear earlier if we want the model to stop. Whereas if our budget is bigger, then we have a specified number of ignores where we ignore the end of thinking token when the model tries to generate it, like here after the number of hours in Raspberry is 2. And instead, each time we ignore it, we just append the wait string. And this very, very simple technique works surprisingly well, as shown in this simple example. And we'll have some more scaling plots later to see how it extrapolates.
Yeah, do you have metrics later to show like the ROI on it later? Yeah, because like sometimes you could imagine that asking it to continue to think doesn't necessarily generate better outcomes after a certain number of minimum iterations.
Yeah, it does eventually flatten out. And that's what I'm very excited about for future research, how we can fix that. But for now, it doesn't scale into solving the Riemann hypothesis quite yet. Yeah. Cool. And while budget forcing is our main method, we also investigate and propose two other test time scaling methods. The first one is conditional length control, where it revolves around conditioning the model on a specific length we want from it. Specifically, we just put something in the prompt, and that could either be a specific token count or a step count or just a generic statement, please think for a long time or please think for a short time. And then the second alternative method is rejection sampling. And this is not a method that we can actually use at inference when users are using this model, but rather a post hoc method where we just sample as many times until we get a specific test time compute setting with some temperature, so the model produces reasoning traces of different length. And then we just pick the one that fits our predefined requirement. So it's an oracle in a sense where we will get the exact test time compute setting we want, but it's not the way we'd like it because we don't have a priori control over the setting. So these are the three methods that we'll explore. Great. And we have three metrics that we use when comparing test time scaling methods: control, scaling, and performance. And we believe that these three are the key metrics that we should care about when we look at test time scaling methods. The first one, control, means we'd like to be able to control as precisely as possible how much test time compute the model is going to spend in its response. So we would want to tell it something like, think for 1 hour, and that's it, similar to an exam at high school where you've got a specific amount of time. The second one, scaling, is that the more time we give the model, the better its response should be. So we want there to be a positive slope in this plot on the right-hand side. So in this case, the plot has nice positive scaling. And the third one is performance, which is simply the max performance that the model is able to reach. And of course, that one should also be as high as possible. So all three of those should be as high as possible. Performance here would just be, I think, around 80 or whatever the model on the right reaches. So the max it can get. Control, scaling, and performance. Great. And with that, I think we can go into the training of our model, the test time scaling results, and more. So any more questions, feel free to interrupt.
Like, hi, Nicholas. It's like, for the budget part, it's like, could you maybe explain more details about it? How is like the number of times you inject the weight into the response, or is it value for it, or just a?
Yeah, that's something that you can predefine. So you can set it to 1, 2, 3, 4, but we find that eventually it flattens out because if you keep appending weight and weight and weight, eventually the model goes completely crazy and doesn't know what's happening anymore. But a few times works quite well, but in the limit, it does flatten out. So I think the best value is somewhere between 2 and 6. Yeah.
Okay, cool. And in the plot you show, like on the x-axis, it is the number of tokens used in the test time compute, or?
Yeah. So in this plot here from OpenAI, we don't know what the x-axis is precisely, but in our plots, I will tell you exactly what it is, and they're all open source and reproducible.
Okay, cool.
Great. Okay, exciting. Let's go into training. So in line with the theme, our training is very simple. We take a Qwen 2.5 model, specifically the 32 billion one, which has already been pre-trained and instruction tuned. And then we train it on 16 H100s for just 26 minutes. So super quick. If you rent these GPUs right now, it would probably cost you around $20 or less to perform the training. And before going into the results, I want to briefly compare our approach to some other contemporary approaches because the field is very hot. So I think there's one category of models which are the SFT/distill models, and this is where we're in because this is also the simplest regime. We just distill existing reasoning traces and just SFT on them, supervised fine-tuning. It's relatively simple. And besides our models, there's R1 distill, SkyT1, bespoke strators, and several others. And the way these differ is usually in their sampling strategy. So where do the samples come from and how many are there? So ours only uses 1,000. The other here use a lot more. And then there's models that also use RL, most prominently probably R1, and several other models where it's unclear what exactly they use, even though for O1, I think they mentioned in their blog post that it is reinforcement learning, but we don't know whether it also involves SFT or not. Okay, and so here's a first plot on reasoning performance. On the y-axis, we have accuracy on Math 500, which is a very common competition math dataset with very hard questions. And on the x-axis is the number of examples that these models used during reasoning training. So on the very left upper side, we have the S1 models, which only use 1,000 samples. That makes them super simple to train and the most sample efficient among the models here. And there are various other models, Bespoke, SkyQ1. R1 Distill uses quite a lot of samples, 800,000 according to their paper. And then there are some models where we don't know the exact number of examples on the very right. And S1.1, which comes back to the distilling slide we had earlier, uses the same recipe as S1, but uses R1 traces instead of the Gemini traces that we used for S1. And we found that this leads to significantly better performance, even though it was the same, roughly the same cost as training S1. Interestingly, it's even slightly above R1 Distill, which is the distilled version of R1 that DeepSeek produced. And they used 800,000 samples, and we were able to get there even slightly better with just 1,000 samples. Great. And that was the first part. So thinking back to what was exciting about the O1 blog post, it was reasoning, and the second part, test time scaling, so that performance improves with more test time compute. And so this is how the test time compute scaling looks like with S1 and budget forcing. On the y-axis is our performance metric, which is accuracy in all these cases. And on the x-axis is how we scale test time compute. And the way we measure it is in average thinking time in tokens. So this is the length of the reasoning trace. We ignore the answer generation and also the length of the question here. And on various tasks like math problem solving, competition math questions from Amy, and really hard questions from GPQ8 Diamond, more thinking time always leads to better performance. And I think what's exciting here is that not all of these dots are like just cutting the model off earlier, but quite a lot of them are about this extrapolation where we just append weight and then the model thinks for longer and is able to fix its current potentially incorrect answer. Okay, so let's zoom in into one of these plots to get more details on how it's working. So this is the middle plot here on Amy, and I've annotated each dot in this plot. So on the left, the dots are just using the cutting off or early exiting part of budget forcing. So for example, for the second dot here, we're forcing 2048 maximum thinking tokens. So after the model has generated for a maximum of 2048 tokens during its thinking part, then we cut it off. Specifically, we just append the end of thinking token delimiter and thereby force the model to proceed to its answering phase. Because from training, the model knows that whenever there's the end of thinking token, then it's answering time. And it'll be something like, my final answer to the question is this and that. So this is a nice way to force the model to transition to answering. And we again do this for 4096. And worth mentioning here is that if the model finishes earlier, if it only needs 500 thinking tokens, then nothing happens. We don't cut off anything, and it just proceeds as is. And then toward the right are the various extrapolation settings. So the third dot from the right is forcing the model to ignore the end of thinking token delimiter 2 times, and instead we append weight, and then 4 times, and then 6 times. And for 2 times, we still see quite a jump compared to the dot before. And then again, from 2 to 4, there's another small jump in performance. But then from 4 to 6, performance remains exactly the same, which is because eventually this method flattens out. Because if we ask the model, if we append weight at the end of its current thinking generation, then it'll try to fix its current mistake, or it'll try to find a mistake. And if we do this multiple times, eventually it just goes back to the same mistake, and it's like, oh, well, I already checked this, and it's fine, or it's not fine, and already fixed it. So there's not as much room to continue scaling with this method. But it does scale initially. And another interesting aspect here is that if the model is already wrong, it usually does not change its answer into something incorrect. So even though we append weight, and it might already be at the correct answer, then it'll just be something like, wait, let me double check this. Seems like it's already correct, or something like this. So it'll go through the reasoning once more and find out that it is correct. And I think part of the reason this works so well is that presumably it is easier to verify than to answer a question. So when the model does weight, then it's relatively easy for it to verify whether or not its current answer is correct or not. And it's much harder to generate a correct answer from scratch. So it's a bit like the PNP problem. And so whenever we append weight, essentially we force the model to verify whether or not it's currently correct. And this is somewhat an easier problem for the model than having to regenerate from scratch or figuring out the answer in the first place.
Yeah, I think at the limit, you would say, like, if you just had a question, you only let it output, like, say, 2 tokens, like 48, then there's just nothing to attend to, right? And the longer you have, the more you can attend to. But at some point, attending to more tokens in the logic doesn't actually help you much.
Yeah. Yeah, I think that's a great way to put it.
Just a question. When it flats out after, we said, like around 4 to 6 times, is this number doesn't depend on like how complex is the question or how difficult is it?
Good question. So it does change from benchmark to benchmark. So for Amy, I think the best setting was forcing 4 times. Meanwhile, for GPQA, I think it maxed out at 2 times, if I'm not mistaken. So there's definitely some differences there. And also, there are differences probably within Amy for the different questions. So we just apply it uniformly for all questions in Amy, which is 30 questions in this case, but you could probably do better by only doing it for very difficult questions or something like this.
So the number here, the 6 here, or the 4, this is the average over all the data set?
Oh, this is the same for all samples in the data set. So we have 30 samples in Amy 24, and for all of them, when the model tries to finish its reasoning trace, we append weight 4 times, for example. And then we average the performance of all of them to produce this respective dot. Does that make sense?
Yeah, thank you.
Hi, Nicholas. I have a follow-up question. So do you see like the types of problems where this 4x and 6x will make a bigger difference? And those problems there, if you scale further, it doesn't like help at all? Asking because there may be problems where, as you mentioned, like verifying an answer is surprisingly easy, like some types of optimization problems, or like a Nash equilibrium. If I give you one, it'll take a few seconds, you will realize it's a real answer. But if I want to figure out one, it will take days probably, and I can't even, right? For those, perhaps if like enumeration or exhaustive search will help a lot, and then scaling up will help a lot. While for some questions, maybe scaling up doesn't help at all, like this type of different categories.
Yeah. Unfortunately, I'm unable to break it down into question types. One part of the reason is that for Amy 24, it only has 30 questions. So these dots here are differences in 2 or 3 questions. So it's hard to say for what kind of types it works best. But I think your intuition makes a lot of sense to me that there are certain types of questions where this should work better. And it would be very exciting to explore that, I think. Another thought is that if you look at the reasoning traces of these models, often they do look a lot like search. The model is just trying a bunch of things and then sort of maybe sometimes more by chance than by actual reasoning capability, it hits upon the right answer. I guess this is also part of test time scaling, just search more.
I see. So I have this conjecture of if you ask a model to solve a Sudoku or some kind of combinatorial problem, a weaker model will just do exhaustive search and then figure it out if you scale it up a lot. A stronger model might try to figure out like symmetries and try to do some reduction and then, you know, solve it much more like cleverly, but then they both would arrive at the correct answer and then they can verify them very easily. Like anyone would be able to verify them, but I haven't seen anything like that. It's something.
Yeah, I think that's exciting. Figuring out when you should go down this search pipeline, pure search, versus like sort of a more reasoning-based approach. Yeah, probably somewhat different. And depending on the question and depending on the capability of the model, you want to go down one or the other, I think. That's very exciting.
Thanks.
Cool, thanks. Okay, yeah, feel free to interrupt if there's anything else. Let's go further.
I have one quick question.
Oh yeah, go ahead.
I think it's a very interesting approach, this interrupting termination, basically by forcing it to rethink. But do you have any ablations in your paper where you kind of try to isolate the effect of your special training set on which you do supervised fine-tuning, and this particular technique that you actually make it stop? Like, would the same technique also work with other, let's say, less optimal training sets, or is the secret sauce also really depending on the special training set, like this very fine-grained diversity that it has, for example, how crucial it is?
We have verified that it works with both S1 and S1.1, which are two models trained on different reasoning traces and answers, even though the questions are the same. We haven't tried it with a data set of different questions, though I've seen other people trying this budget forcing approach and it has worked for them, but I don't have exact numbers on it, unfortunately.
Great, thank you.
Thank you. Great. I want to take one step back and think about at a high level, what is test time scaling? And I like to group it into two different approaches. One is sequential and one is parallel. And for sequential, the idea is that we have one continuous scaling paradigm where the model continuously works on its answer. And that is something like the COT, where the model kind of reiterates on its current answer and builds on intermediate results and so on, versus parallel, where we just generate multiple times independently in parallel. The classic example of this is majority voting. And then at the end, we somehow aggregate the answers. So in majority voting, we just take the most common answer. And usually that's better than just taking a single generation. And while these paradigms can be used together, they're not mutually exclusive. Generally, intuitively, I think that sequential scaling is more promising because with parallel scaling, the model might make the same mistakes in its independent generations and waste a lot of test time compute in that sense. Versus with sequential, you have one continuous string, and ideally it doesn't make the same mistakes, but rather builds on its previous mistakes and intermediate results and can continuously improve. So these are sort of the two high-level paradigms, but they can definitely be used together. But this intuition that sequential should be better is partly verified by this plot where we show that sequential scaling, which is just letting S1 generate a longer or shorter chain of thought with forcing, like changing the length of its reasoning trace, has a better scaling slope versus just parallel scaling via majority voting on our base model, which is Qwen 2.5 32B instruct. So both of them scale with more test time compute on the x-axis, more total output tokens, but sequential scaling has a better slope, even though it eventually flattens out, but hopefully we'll solve that in the future. Great. Now I want to go into some data ablations. So previously we covered our three key filtering steps for creating S1K: quality, difficulty, and diversity. And here we perform one ablation to validate each of them. And we benchmark these ablations on our three core evaluation sets: AMY 24, which is math, math 500, which is also math, and then GPQA Diamond, which is a lot of PhD level science questions from various subjects. And the first setup is 1K random. And for this setup, we simply take 1,000 random questions. So in a sense, we disregard any quality filtering and also the other filtering steps and just take 1,000 random. And that one leads to significantly worse performance on all three benchmarks compared to our final data set at the bottom, S1K. Then the second approach is, what if we only care about diversity? So we disregard our quality and our difficulty filter, but we just make sure we get the 1,000 most diverse samples from very different fields. And that one is also pretty poor, especially on AMY 24, because probably now we're not getting as much math as well. But even on GPQA Diamond, which is a bit more diverse in its question pool, it is much worse than S1K. So this is also not a good subset. And the third ablation here is 1K longest, where we say, okay, let's only take the 1,000 samples with the longest reasoning trace, which is a proxy for the difficulty of this sample. So we say that, okay, let's only look at difficulty and disregard diversity and quality in a sense. And while this one is pretty strong on GPQA Diamond toward the right, 59.6, it is relatively poor on math and AMY, so also not really better than our S1K selection. And our final comparison is just taking the entire pool that we created of 59,000 questions, and even that one is more or less equal to our S1K selection. So the takeaway here is, I think, we can go a very long way with these three key filtering steps: diversity, quality, and difficulty, especially when they're used together. Like using only one of them, like only diversity, does not lead to better performance, or using only difficulty, which is sort of the longest subset, is also not that great. But if we use all three of them together, difficulty, quality, diversity, which creates our S1K data set, we get really good performance that's more or less on par with the full 59,000 questions. And of course, it's much cheaper to train on those 1,000 than the full 59K.
Curious, I mean, maybe it's just I guess maybe it's noise, the 92.8 versus 93, that the 1000 actually outperforms it, but I guess that's the error bars, the minus 2.6%.
Yeah, there's definitely some noise here, yeah. So we added some error bars, but yeah, especially for Amy. So Amy 24 is only 30 questions, so that's why we need to take these numbers with a grain of salt. Yeah.
Thanks.
So for comparison with the 4 data set, it's like you control them to or train by one epoch, or?
We train all the setups with 1K samples, so 1K random, 1K diverse, 1K longest, S1K, with the same training hyperparameters, which is 5 epochs.
How about for the 50K one, 59K one?
For the 59K, I don't know it off the top of my head, but it is, I think, more than 1 epoch or 1 epoch. The weights and biases of this one should be available. If not, then let me know and I can make it available, I think. Yeah.
Okay.
Yeah. But we tried to make sure that the hyperparameters among all of them are as similar as possible. So as I said, for the 1K runs, it's pretty much everywhere the same. For the 59K, it's hard to make it the same because it's a much bigger data set, but it is more or less the same to make sure it's a fair comparison. Okay, great. Then after the data ablations, I want to go into some of the test time scaling ablations. And if you recall previously, we discussed 3 key metrics that we care about with regards to test time scaling. We want good control, being able to tell the model ahead of time how much test time compute it has. We want good scaling, meaning that more compute leads to better performance, a positive slope, and we want great performance at the end. And so we benchmark these 3 metrics here across the various methods. So we have budget forcing, which is our main method that we use throughout the paper, but also the different conditional control methods, token, step, class, and rejection sampling. And so at the top, budget forcing has perfect control because we're literally forcing the model to think for longer or think for shorter with a precise token limit that we can control. And that's why it's 100% at control. The scaling is positive, as we've seen in the test time scaling plots we looked at. More test time compute leads to better performance. And the final performance here, this is Amy 24, was 56.7 that we were able to reach with forcing weight for multiple times. And then the second part in this table are the various conditional control methods. So TCC is token conditional control. And this one actually does not have good control. So a reminder here, we are telling the model in the prompt, you've got X amount of tokens. Please think for that long. And it never really follows that prompt. So we might tell it you have 1,024 tokens, but then the model just thinks for 5,000 or whatever it wants, even though we train it with this conditional control method. So during training, we will tell the model you have 1,024 tokens, up to 1,024 tokens, and then the thinking trace that follows will adhere to that limit. But then at inference, the model ignores that and might just think for much longer. So it does not have great control. The scaling also was not clearly positive in our experiments, and the performance also not great. We tried combining TCC with budget forcing. So we tell the model you have 1,024 prompts at 1,024 tokens, and then if it tries to think for longer, then we'll just force stop it at 1,024. And of course, in this case, we get perfect control 100%, and the scaling will also be better, but performance does not match the budget forcing baseline. And then the next 2 are step conditional control. So here, we thought that maybe tokens is too fine-grained. The models aren't able to count their own tokens, at least not the models that we were dealing with. Maybe it needs a whole nother level of capability for models to be able to do that. So can we go more coarse-grained and partition multiple tokens into steps? And the way we do this is we just separate the thinking traces that we train on into steps based on new lines. And I tell the model you have X amount of steps, and this is what is going to be in the thinking trace. And this one has slightly better control than token conditional control because the model is much easier for the model to count the steps than the individual tokens. And the scaling is even slightly positive, but performance is still not much better. And then again, here we can add budget forcing on top of it to make the control perfect, but it won't improve performance in this case. And finally, CCC is class conditional control, where we just tell the model, please think for a long time or think for a short time. So breaking it down even further into a much more coarse-grained scenario. And that one also doesn't have great control. Scaling is quite good. So it does actually work. We can tell the model think for a long time, and it does think for a longer time than if we tell it to think for a short time. But performance does not catch up. And then finally, we have rejection sampling, where, again, this is not a method we'd want to use in practice because it does not work with control a priori, but just post hoc, we take the sample that fitted the control requirement. And of course, we'll get perfect control by design because we sample until we get perfect control. But interestingly, with rejection sampling, scaling is negative. So even though we have perfect control and we have these thinking traces that are longer and longer in their, they have longer and longer reasoning, the performance of them gets worse and worse the longer they are. And the best performance is only 40. And I have a plot on this that I, yes.
Just a reminder, so we only have 3 minutes left.
So. Oh, yeah. Yeah, I think that's, I can go over the rest pretty quickly. Yeah. So for rejection sampling, we have a quick plot here, and this is how it looks like. So the more thinking time, the worse the performance. And there's more details on this in the paper, but I think it's a quite interesting case of inverse scaling. Great, and then here we tried some additional strings rather than weight. The takeaway is that weight works the best. And finally, I wanted to finish with some of the limits of this current paradigm, which is that eventually it flattens out, as we've seen, and also models run out of context window. And one preliminary way to scale further is by combining the sequential scaling with parallel scaling, as we've mentioned previously. So we can use majority voting or rebase, which is a bit more advanced and uses tree search. And this significantly improves performance and allows us to scale beyond a fixed context window. So here, sequential scaling performance drops because our model just runs out of context window and tries to think for too long. But with parallel scaling, we can scale further and improve performance. And this is it. So a minimal recipe for reasoning and test time scaling. And we're excited to push this further. Thanks a lot. Everything is open source, and happy to answer any more questions if there are any.
Yeah, thanks a lot, Niklas, for the great talk.
Thanks.
I think based on the chat, a common question is about your base model. So how do you select base model?
Yeah, so we took Qwen 2.532b instruct because it's the best model on math tasks that we could find that was open source.
Any other question from the audience?
Yeah,
Yes.
one more question. It's like that the S1 dataset also works for the smaller model, like Q1 7b or even more smaller. Yeah.
On our GitHub, there's one issue where someone tried it with 7b and posted their results there. We haven't tried it, and I haven't seen as strong gains, but I think they did put forth some gains. So yeah, if interested, maybe you want to take a look there.
Okay. Yeah. Another question is like, do you think S1 or the distillation is necessary? Because we see some report they just show, for example, using reinforcement learning only to achieve the similar performance. So how do we compare these two approaches?
So not distillation, but what do they use instead?
The reinforcement learning 0. For example, tuning from scratch using the reinforcement learning.
Oh, I see. Yeah, if you want to do reinforcement learning, then I guess that's a fundamentally different pathway. So here, our goal was to look for the simplest possible way to get these two results using a test time scaling. And if you add reinforcement learning, I think it does add a lot of complexities, but could ultimately lead to much better performance. But if you want to do something very simple and minimal, then probably distillation is the way to go.
I see. Yeah.
You mentioned earlier that sometimes scaling is beneficial, even though the model produced wrong answer, because it improved the reasoning of the model. So how did you evaluate that the reasoning is improved? Like, how did you evaluate this?
Yeah, when we refer to reasoning, we mean these three benchmarks, so AMY, Math 500, and GPQA Diamond. So we think that they capture reasoning performance because they're very hard math questions that require a lot of thinking potentially. And yeah, so that's how we sort of hill climb reasoning, if that makes sense.
Like you go through the reason, like you evaluate it manually? Like how do you, like despite that the answer is wrong, like how do you say that the model is better now? Oh, do you mean the answer is wrong on one of these questions? I remember you mentioned earlier in the talk that scaling is beneficial in some cases, even though the answer was wrong. Oh, I see. Maybe that was when I referred to our data set, where some answers in our data set that we train on are wrong, and we don't find this to be a major problem. Yeah, because it is more about learning this formatting and how to reason rather than these actual question-answer mappings. Oh, okay. Thank you. Thanks.
Yeah, maybe I have a question about the data set. So I think this 1,000 data set is very interesting. So if you have a chance to get another 1,000 or 10,000, what's your ideas?
I think we could not make the diversity one as strict. So if I go back to this one, to go from 24K to 1K, essentially we said, okay, we want 1K. So let's just diversity sample until we got 1K, until we filled up this number. Instead, we could have just said, let's do 10K and diversity sample until we got 10K. So I would just probably start there. And beyond that, maybe there are other ways to extend it, though I'm unsure how much more gains we can get by increasing the quantity. Definitely some, but in this plot at least, R1 Distill uses 800,000 training samples. And on Math 500, it is actually even slightly worse than S1.1. So this might not capture the entire performance of the model, and probably is better on some other benchmarks. But nonetheless, I'm unsure how much more samples can help. Definitely more samples of top quality are better than not having them, but unclear to me how much.
Got it. Thank you.
Thanks.
Yeah, thank you for the talk. So Nicholas. Yeah.
Okay, thanks.